So in an earlier recording I speculated that the power good pin, which comes from the PSU, I think it's on this pin here, was likely used by the MT004 and in some way would connect to the reset input. I think I've seen that configuration elsewhere and I wanted to check that, so I got hold of the PCB and used my Fluke multimeter on the continuity range, which beeps when there's a very low resistance, and tried to buzz out the circuit, as it's called. And this video will give an idea as to what I found. Now here's the way I decided to go about it. First of all, in my notebook here I've drawn some of the components more or less in the same positions as the components over here. So we've got the 2 resistors, the 3 capacitors, the tantalum electrolytic capacitor, 2 more resistors, a diode, another resistor, and we have 2 jumpers, jumper 1 and jumper 2, and we can see those over here. And that's how the circuit started off, and using the multimeter I made best guesses as to what the connections to those components might be. An obvious starting place is to look for any connection from either end of the component to either ground or 5 volts. Now that pin here and here, they're ground, they're easy to find, and this pin here, because it's pin 20 of this IC, I know that's plus 5 volts. So it's easy to get a connection for one of the leads of the multimeter for power and ground, and then the other lead is used to poke these pads here. There's a little bit of crust on top, as you can see, so sometimes you just have to scrape away. I would also, when making a connection, check each of the pins of the clock generator IC, because this was a likely destination and connection of some of the components here. And eventually I managed to determine the connections here, and I guess it's called TL:DR, is the power good pin, as far as I can tell, doesn't appear to go into the circuitry and doesn't connect to this chip here. However, jumper 1 appears to be, rather than a jumper, a connection for a reset switch. So if we look what's going on here, we see some of the components is to do with the keyboard clock and data. This is the 5-pin DIN for a connection to an XT style keyboard, not a PS2, that's a totally different connection. And I had to trace a little further into the circuit, well over here onto the right hand side, looking at the IBM PC schematics to get an idea where the pins might go, and we see them go to the type of places that we might expect. Jumper 2 is interesting because it comes from one of the I/O pins of the 8255 PPI parallel I/O and goes back to the 74LS322, which is a shift register used for receiving data from the keyboard. I took a look on the IBM PC schematics and it sort of makes sense. I'm not quite sure what that jumper does, but on the PC schematics that is a direct connection. So for some reason it can be useful to have that connection broken. I don't know why. These 2 resistors are interesting because we can see that one of them comes from the clock output of the main clock generator IC and goes to the CPU. Now when I was working on my own CPU board with the 8088 and the same clock generator IC, I found that the clock generator IC had a very fast rise and fall times, resulting in overshoot and undershoot at the nearby CPU, but more worryingly further across the board, where there was a trace of several inches, where the clock was used by a GAL chip, there was significant overshoot and undershoot. Now my thought was that a series resistor would actually help eliminate that, because we'll effectively get an RC delay. There's some capacitance on this wire here, and together with that resistor it's just going to so-called take the edge off that sharp rising edge, and that will result in less overshoot and undershoot. And we see the same thing was done on the OSC pin. So again, we have a small resistor, and the other side goes to the common pin on all the ISA slots, which is the OSC pin. So we know that's 14.318 megahertz. Now this circuit here is easily recognizable. A diode and a high value resistor across it going to the not reset input of the clock generator IC, and the not reset input is Schmitt triggered, together with the electrolytic capacitor down to ground. This is a classic power on reset circuit, and using jumper 1, if that's shorted to ground, that resets the processor and the rest of the system, and when the reset switch is released, the voltage on this capacitor ramps up via the 1 mega ohm resistor, and the reset goes inactive, and correct operation is guaranteed because the reset input, or the not reset input, is a Schmitt trigger input. So this is most of this circuitry understood. Again, we've got the same type of idea. The signals coming back from the keyboard, clock and data, we have a 4K7 and a small capacitor. I'm not sure what the value of that capacitor is, but again, that's likely to try and just mitigate the effects of any high-speed edges and any signal integrity issues that could arise. At some point in the future, perhaps I can put a scope on there and we can take a look and see what those signals look like with respect to the rise and fall times. That's reasonably high, but if that's a low value capacitor, it's not going to really have a big effect, just enough to reduce any really fast edges coming out of the keyboard. Now, further down here, I did a little bit more investigation, but that's in an area of the PCB that isn't shown here. I did speculate that there's a pin on the clock generator IC, pin 13 here, which selects between the internal oscillator and the external clock input. The external clock input comes from a 24 megahertz crystal and 74LS04 combination, and so there's a square wave comes in on the external clock pin, and a 14.318 megahertz crystal connects to the two crystal pins of the clock generator IC and generates the internal crystal oscillator signal. And inside the chip there's a multiplexer which can select between the two clock sources using the F/C pin. Now, I speculated that would go to a jumper marked turbo on the other side of the motherboard, and I attempted to buzz that out and there was no direct connection. So I did a little bit more investigation and came out with this surprisingly complex circuitry. This is a turbo jumper to where you can connect an external lock-in switch. It's either locked on or unlocked off. In other words, it's not a momentary switch. It has a 5 volts pull-up resistor. The other side goes to ground, and then it goes into several inputs of NOR gates. Now, I tried to work out the truth table of this, and it seemed to be exclusive OR. The connection that I wasn't expected was an output, an I/O output of the 8255 PPI, pin 20, port B2. Almost certainly that's going to be an output. And my speculation is that is turbo control, which can be controlled by the CPU. The CPU can write to the 8255. And again, I might speculate that there's a keyboard combination that if you press is recognized by the BIOS and will set PB2 either high or low depending on the key press combination. I have no idea what this is, and I'm sure I can Google to get some ideas as to whether there was a standard combination of keys, Control Alt plus, Control Alt minus, something like that is likely to be the case. but it goes through the logic of the NOR gates, and then it goes into a D-type flip-flop. So this almost certainly is to allow the clock to be switched while the CPU is running. We never want to switch a clock asynchronously to either of the two clocks, because we could get what's called runt clock pulses. These are clock pulses that are too thin, and a clock pulse that is too thin can upset circuitry it's connected to, particularly a CPU, and can cause strange things to happen, and could of course cause the CPU to crash or do something strange. So the right way to do this is to somehow get the FC input to change when the clock is low. So the clocks are pulsing high, the clock goes low, the multiplexer changes, and then the next clock is one of a different frequency. So there's a clean switchover. I didn't trace where pin 11 goes, but it's highly likely it goes to either clock or one of the similar pins coming from this clock chip. So that's this circuitry. It's given me a little better idea as to what's going on in it here. It was quite interesting to do. I don't want to reverse engineer the whole of the motherboard, but at least now I know if I want to do some experiments and I want to do a reset and capture the behavior of the some of the signals on the CPU, for example, on the scope, I now know if I connect a switch here I can force a reset to happen. I hope that was of interest.